Hi, welcome back to Moose and Chemistry. This is electron configuration of tungsten. W lesson. Tungsten W? Ooh. Do you know what? Some of these elements are like named back in medieval times. Or a little bit later than that. And they had original names like tungsten wasn't always called tungsten. It actually was called wolfram. Wolfram, that's right, yes. So anyway, so they just kind of kept the letter, but then they changed the name. Alright, so anyway, so let's go ahead and get started here. So tungsten, or wolfram, I like to call it, is element number, of course, 74 on the periodic table. And its atomic mass unit is 184 AU. So that means it has 74 protons, 74 electrons because it's electrically neutral. And remember, to get neutrons, you simply go AMU minus the number of protons equals neutrons. So you go 184 minus 74 gives me 110 neutrons. So we're going to put 110 right there. Okay. So now we're just going to clean this up a bit here. Yeah. Alright. So now remember that the S suborbits can hold 2 electrons. The P suborbit can hold 6 electrons. The D suborbit can hold 10 electrons. There we go. And the F suborbit can hold 14 electrons. Got ahead of myself there, but that's okay. I'm having so much fun with this. The off-ball principle means that we fill the lower shells first before we fill the upper shells, and we use something called the diagonal rule. And there it is. Okay, we're going to follow these orange arrows down until we run out of electrons. How many electrons is that going to be? 74 electrons. Pretty simple, huh? It's very simple. It's very straightforward. So let's go ahead and do this. So we go 1s2. Okay, there's 2 electrons used up already. 2s2, now we've used up 4 electrons. See how easy that is? 2p6, 3s2, 3p6, 4s2, it's just a pattern, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, yep, and last but not least, 5d4. And now you have used up 74 electrons. Pretty easy, I gotta tell you. Alright, now let's look at Hund's rule. Hund's rule says you have to put an up arrow in every suborbit of that suborbit, and then you can put the down arrow in that suborbit. And that's dealing with orbital notation. So we go up arrow, down arrow. See that? And that talks about the spinning of clockwise and counterclockwise electrons. Clockwise for up arrow, counterclockwise for down arrow. So up arrow, down arrow. Here comes a classic example. How to explain Hund's rule. Now you have 2px, 2py, 2pz, right? 1, 2, 3. Now the down arrows. 4, 5, and 6. Amazingly easy. Okay? Up and down. See that? This is just beautiful. And then, of course, we have the 3dx squared minus y squared ones. We have 5 of those in this area here. And then we just put our down arrows. And then uses up 10 more electrons. Oh, this is so much fun. I mean, really, seriously. And it's not like coloring, a coloring book or something. You don't have to stay between the lines. If the arrow's a little bit off, that's okay. All right, here we go. Again, another 10 electrons going to be used up here. Wow, it's so easy. See how I'm following Hund's rule? Not a big deal. And this one's going to have 7, so for the first half, then it'll have 7 for the down half. Yep, there's 7 arrows. Now 8, 9, 10, 11, 12, 13, and of course 14. And that takes care of our 4F, right? And then we have 4 5Ds. So 1, 2, 3, 4. Okay. Now, let's look at our noble gas notation. The nearest noble gas to Wolfram is xenon. You can't use radon because that's afterwards. And we know that xenon ends in 5p6. So go ahead and take care of all this right here. And that's xenon. So that just cuts all that out. Now some people like to go 6s2, 4f14, 5d4. But I've done a lot of research, and the more correct way actually is 4f14, 5d4, then 6s2. So it depends on what your instructor wants you to use. You can use this backwards way, or you can use what I consider the more correct way. It just depends on your instructor. Now, you would be tempted to think that Wolfram, aka Tungsten, is in the 6th period, but it's not. It looks like it is, because it's in the D block. It would be n-1, so it is 6 minus 1, and that's going to give you 5 for your energy level, right? Principal quantum number is 5. It's in the D block, so your angular momentum number is 2. Your magnetic number is going to be 1, because it's the 4th point over. Whoops, I meant to put that there. Sorry about that. See, I'm having too much fun, right? Alright, so you got the 1 there. And our last arrow, guys, is going up. So it's going to be 1/2 positive. Don't you love it when you mismark something? It's amazing. But anyway, you guys have be fun, you'd be snarly, and we'll see you back here at Musin Chemistry.